Hello dear students, this is Dr. Aisha Nazuk here. Welcome back to my channel Hub. Those of you who have landed first time of the channel, you are more than welcome to explore my playlist on probability theory, introduction to econometrics, statistics and much more. Today's lecture is focused on normal distribution, which is relevant to chapter 7 of the book Douglas Lind. My regular viewers are well aware of the fact that in this playlist of probability distribution, I have advised all my viewers to download the book authored by Douglas Lind and other. You can easily download the 9th edition of this book from the Genesis library. If you haven't explored the Genesis library so far, you are more than welcome to type how to download books from the Genesis library and my channel name Hub. This will take you to the video where I have explained how to use the Genesis library. If you post a request in the comment section, I can also add the link of the Genesis library in the comment section. Anyhow, so we are focusing on chapter 7 of Douglas Lind book, and the topic for today's lecture is normal distribution. Normal distribution is the first time it was discussed by a German mathematician and physicist called Friedrich Gauss. So it's sometimes also called the Gaussian or the Gaussian distribution. Pardon if I'm not pronouncing the name correctly, but anyhow, so the Gaussian distribution is a bell-shaped distribution. Just to help you understand with the help of this friendly image, you can see that a distribution which is bell-shaped is normal, and a distribution which is not bell-shaped, any distribution other than the bell-shaped, is not normal, right? So you can see that this bell-shaped is talking to the other non-bell-shaped and saying that I like you but you're not normal. So with the help of this image, I have tried to explain that normal distribution is bell-shaped. Okay, so now we will be focusing the key properties of normal distribution. As I have already told you that it's a bell-shaped distribution and it has a single peak at the center of the distribution. So you can see that the peak or the maximum height is in the center of the distribution. So this is just the first basic property of the normal distribution. The second property or the fact about normal probability distribution is that it is symmetrical about the mean. Now what does that mean? Symmetry simply means that if you can declare one half as the mirror image of the other half. For example, only bell shape is not symmetric distribution, but bell shape is also one possible symmetric distribution. We can have other type of symmetrical distribution as well, but the basic definition of symmetrical distribution is one half is the mirror image of the other half. So you can see this bell shape. If I impose a line here on the center, which I declared that on the center we have the average value or the mean value. So in the center we have the mean value, which is denoted by the Greek symbol read as mu. So this is the Greek symbol and it is read as mu. So this is the center of the normal distribution. And how is it symmetric? For example, if you fold the one half of this image by using this line, so then this become mirror image. If you don't understand this concept, just take your hands and fold your hands up onto each other in such a manner that your pinky finger collide with the pinky finger and the other finger, the index finger collide with the index, and so on, the thumb collide with the thumb. So we say that without any disrespect to different type of people, in general human hands are symmetric because one half is approximately the mirror image of the other. In other words, one hand is the mirror image of the other hand. They are so much similar. So we can say that it's a symmetric distribution. So similarly, if this line here, this line, if you fold this bell shape by using this line as the center, so one half shape of the bell will superimpose on the other half. So the normal distribution is symmetric about mean, or it falls off smoothly in either direction from the central value. So this was the second key fact about normal distribution. The third key fact, that the location of the normal distribution is determined by the mean mu. So if I, for example, change, let's say the mean of a distribution, normal distribution is 0. So this middle bell shape, this is a bell shape or the normal distribution having mean equal to 0. If I change the mean to, let's say, -10, then the bell will slide backward, right? And for example, if I change the mean to 20, then the bell will slide forward. So if I change only the mean of the normal distribution, then what happens? We have a horizontal shift, or the bell keeps sliding either backward or forward. If the mean increases, it slides forward. If the mean decreases, it slides backward. So that's why we say that location of a normal distribution is determined by its mean or the average value mu. Next key fact is that the variation or the dispersion of the distribution is determined by the standard deviation sigma. So we know that if in a distribution there is lot of variation. For example, if you just analyze data of different people, let's say their salaries, and if there is a lot of dispersion, then the bell will be wider. If there is lesser dispersion, then the bell will be compact, because you can simply understand if there is lot of variation in the salaries, then some people may be here on the left side, some may be here on the right side, and so on. So the bell will be wider. So standard deviation determines the width of the curve, and larger values result in wider and flatter curves. So if there is more variation, then the bell is wider and flatter, as you can see. So if standard deviation decreases, the bell becomes compact, simply because we have less variation, so the bell squeezes or it compresses. So this was key fact number 4. Next important property or fact about normal distribution is we can have any real number value of the mean mu and any real number value of the standard deviation sigma. So that's why I have shown these two real number lines here. Mu can be any real number between -infinity to +infinity. Similarly, standard deviation can be any real number between -infinity to +infinity. Right? So we can have infinite combinations of mean and standard deviation, because how many possible values of mean are here? Mean can be any real number, so we can't count. Similarly, we can't count how many possible values for standard deviation are there. So we can have infinite type of normal distribution, each having different type of values of mean and standard deviation. So the normal distribution, the other fact is the highest point on the normal curve is at the mean. You can see that the central value, we started the discussion that the central value is average, but we can see that this central value is mode as well. Why is it mode? We define mode as the value having maximum frequency or maximum occurrence. So here you can see that the maximum occurrence or maximum frequency is here. So this value is mode. And why is it median? Because you can see before this dotted line we have 50% data, and after this dotted line we have 50% data. So by definition, this line is the median as well, because it's cutting this bell into two equal parts. So the highest point on the normal curve is equal to mean, median and mode. So this helps us in coming to the conclusion that in normal distribution mean, median and mode are all equal. So next we come to the notation for a normally distributed variable. If x is a random variable and we want to write that it's normally distributed, so we write it like this: x follows, this slanting symbol is read as follows. So x follows normal distribution, so this capital N is reserved for normal, right? X follows normal distribution with these two parameters, mean, mu, and variance, sigma square. So there are two parameters of the normal distribution. The first parameter, which is written in the bracket, is always mean, denoted by mu, and the second parameter written is sigma square. It is equal to, its variance, and it is denoted by the symbol sigma square. So whenever this notation is written, you must understand that if it is written that x follows normal distribution, so whatever the number in the bracket here occurs first, that is the mean, and the second number which is written here, it is variance. So I have written in general notation. Then next we have probability distribution function of normal random variable. So this is the probability distribution function or the PDF of the normal random variable. So you can see it's little bit complex. If you haven't, for example, if you have earlier on analyzed the PDF of binomial distribution or hypergeometric distribution, you may feel that this one is relatively a little bit complex, especially if you haven't heard about the exponential function earlier on. So if you haven't heard about exponential function, maybe it's high time that you watch basic video about what is exponential function. Only then you'll be able to understand the PDF of normal distribution. So the PDF is 1 over square root 2 pi into sigma square. So pi is a constant which is equal to 22 by 7 roughly. So square root 2 pi into sigma square, where sigma square is variance, exponential function minus half into x minus mu over sigma whole square. So x is the random variable for which we want to make the distribution, sigma square is the variance of that random variable, and mean is mu is the mean of that random variable. So you can see that this is relatively a little bit complex, but no need to worry. In the coming few slides I'll let you know how to easily find out the probabilities without directly using this complex PDF. Before I introduce that concept, let me recall the fact that in continuous distribution, you know that we are dealing with continuous random variable, and we cannot count all possible values of continuous random variable because they are real numbers. For example, if I have to count all real values between 1 to 10, so it's not possible, I cannot count. So in continuous distribution, instead of using sum, we use integration to find the probabilities. So let's say in a normal distribution, mean is 10 and variance is 5, and I have to calculate the probability that x is between 0 and 10. Now we know that we just introduced that the PDF of normal distribution, let me refer back to this slide. This is exactly what is written here. I have copied in the next slide. So the PDF is 1 over square root 2 pi sigma square e raised to the power minus half into x minus mu over sigma whole square. Now if I switch the value of mean equal to 10 and variance equal to 5, then this PDF can be written like this equation which is given here next. So I've simply put in the value of mu equal to 10 and sigma equal to square root of 5. Because variance is 5, so that means sigma or the standard deviation is square root of 5, because we know that standard deviation is the square root of variance. Okay, so this is the PDF and I have to calculate the probability between 0 to 10. So what I am going to do, I'm going to integrate this equation or this functional form from 0 to 10. Now you see that there are two problems. First of all, it's not very easy to integrate this function. Secondly, even if I come up with a method to evaluate this integral, another problem is every time mean and variance changes, the integral must be computed afresh. I mean, you have to do the integration again, because if I change the value of mean and if I change the value of variance, then this entire PDF changes. So researchers have come up with a very important method which is sort of a shortcut. So before we move to that shortcut, the point of discussion in this example was, first of all, to tell you that in continuous distribution we use integration to compute the probabilities. For example, if you have to compute the probability that the random variable takes on the value between 0 to 10, I am going to integrate it from 0 to 10 and integrate what? The function for a given value of mean and variance. But as I have told you that this integral is not that straightforward, so the researchers have come up with an alternative method which is very easy, and for using this method we don't have to directly use the integration. How? First, let me acquaint yourself with the idea of standard normal variable. A standard normal variable is one which follows normal distribution with mean 0 and variance 1. Right? First of all, we acquaint ourselves with the standard normal variable. So how do we standardize? First of all, you should also focus on the fact that why am I calling it a standard normal? Because it may be a method of without using the complex method of integration, we are going to use some standardization technique, and without using the integration directly, we are going to rely on a table and we are going to compute the probabilities very easily. First of all, let me again reiterate that a standard normal distribution is the one which has mean 0 and variance 1. And how do we define a standard normal variable? It is always equal to, so this equation is fixed. This equation is fixed means that we always subtract mu from the value of x and divide by sigma. I mean, for example, if my study variable is salary, and then x is my salary, mu is the average salary, and sigma is the standard deviation of salary. So let's say if my salary is in a given context, let's say $10,000, and I want to standardize it. So I'm going to use the value of x as 10,000 and mu as the average salary. For example, if I know that the average salary is 8,000, so I'll use mu equal to 8,000. Similarly, if I know the standard deviation, of course to standardize you must know the value of mu and sigma. So if, for example, if we link with this example, here mean was 10 and variance is 5. So we know that mean is 10 and sigma is square root of 5. So if I tell you have to standardize for, let's say, x is equal to 2, so what you are going to do, 2 minus the value of mean, which I have already told you that it's 10, and divided by sigma, which is in this case square root of 5. So you can easily standardize a variable by subtracting mu from it and dividing by standard deviation sigma. So by using this transformation, because this is simple a transformation in which we are converting one variable to in its standardized form. So by using this transformation, what happens that the complex PDF, let me refer back to this. So here I have declared that x minus mu over sigma, this is equal to z. So instead of writing this entire thing, if I write this as z, So I can simply write that this is equal to 1 over square root 2 pi. So but where is this sigma square gone? Right, you must think about it. Where is the sigma square gone? I've just told you that in a standard normal variables variance is equal to 1. So when we put sigma square is equal to 1 and we put x minus mu over sigma equal to z, the PDF becomes this equation, 1 over square root 2 pi e power minus z square by 2. So this is the probability distribution function for standard normal variable, and the lower and upper limit for standard normal variable is minus infinity to plus infinity. So let's say we have to compute the probability that standard normal variable takes the value between 0 and 0.51. So although I have already told you that I am not going to use integral, but I am helping you understand how this table is constructed. So this table, by the way, is available in appendix B3 of Douglas Lind book. So if you haven't downloaded the book, by the way, you can easily download the normal distribution table from the internet as well. But if you are using the Douglas Lind book, it's in the last page of that book, appendix number B3. So if you have to compute the probability between 0 to 0.51, so how you are going to calculate? You simply integrate the standard normal variable between 0 to 0.51, right? So we have to compute the probability that standard normal variable takes the value between 0 to 0.51. So if I compute this integral 0 to 0.51, researchers have already computed, integral values for different possible values of standard normal variable. So you can see here in this table the heading is z. So this is set notation that we use z notation for standard normal variable. Here for example we use capital Z. So here in the table we have this z value. If I have to read this table and I have to find the value between 0 to 0.51, this table, as you can see in the image, it is constructed in a manner that the shade, if I read it against 0.51, this will give me an area between 0 till 0.51. For example, if I had read the table against 1.96, so whatever the value that may have come out of this table, that would have been probability between 0 to 1.96. So the table is constructed in a manner that it gives me the value from 0 till a particular point. So if I read the value against 0.51, so you can see in the row I have picked 0.5 and in the column I have picked 0.01 because I am looking for 0.51. So the first decimal place is 0.5. The second decimal place 0.01, so I have read it against 0.01 here, so it gives me 0.1950. So the required probability is 0.1950. So what is the reason that I am discussing this table and I am linking with the integration? It is because of the fact that researchers have computed values of integral for the standard normal variable for different possible values of z, and they have put in the answers in this complete table. So let me show you the complete table as well. So this is the complete table. Just a minute. So this is the complete table. You can see it varies from z is equal to 0.00 till z is equal to 3.0. So why the table is ending at 3, that you will get to know in a while, because in the standard normal variable upper range is 3. If it's not clear for now, don't worry, we will discuss this in coming few slides. Anyhow, so by using this table without using the integral, we can directly compute the required probabilities for the normal variable. So the different names of the standard normal variable are z-values, z-score, z-stat, standard normal deviate, standard normal values, or just the normal deviate. So these are different types of names that you may come across in textbook. So that's, or if you use different activity sheets to solve the questions. So these are the different type of name that could be used for standard normal variable. Okay, probabilities for the normal random variable are given by the areas under the curve. As I've just told you that in the continuous distribution, instead of summing different values, we compute the probabilities by using area under the curve. So for example, what is the area towards the left of the mean? It is 0.5. And what is the area towards the right of the mean? It is 0.5. And the total area under the curve is 1. Why? Because the total probability is always 1. Now we are going to discuss that in this normal distribution, we can construct different types of intervals. And how do we construct? First, I'll refer you to an Excel sheet. Okay, so here what happens, that you can see, let me show you, that will be a smaller font, but for the time being, let me tell you that I have generated data of 34 values. So I have a data of 34 values, and these are the values. Suppose that I want to ask that whether this data fulfills the requirement for normal distribution having mean equal to 1.5 and variance equal to 0.2. So this is, although if you explore, there are many other technical methods for checking whether a data is normally distributed or not, but this is just a basic method in which if you have a series of values, for example here we have 34 values, and we want to check whether we can declare these 34 values as normally distributed with mean equal to 1.5 and variance equal to 0.2. So we need to construct what we call as the 1 sigma limit, 2 sigma limit, and similarly the 3 sigma limit. So what is 1 sigma limit? Refer you back to the diagram. So 1 sigma limit simply means mean minus 1 times standard deviation, and similarly mean plus 1 times standard deviation. So I am talking about an interval. So 1 sigma limit means mean minus 1 standard deviation till mean plus 1 standard deviation. Similarly, 2 sigma limits mean mean minus 2 times standard deviation till mean plus 2 times standard deviation. Similarly, I can also construct the 3 sigma limits. So if I have to construct the sigma limits, I have to use the value of mean and standard deviation which is given in the question. So pardon, I have to this is a typo, I have to type here mean equal to 0.34 and variance equal to 0.18. Of course, if you are solving this question from an exam point of view, of course this is part of the question. So data will be given and you are being asked that can you conclude that this data follows normal distribution with mean 0.34 and variance equal to 0.18. So 1 sigma limit means I am going to subtract sigma from mean. So you can see, if when I am constructing 1 sigma limit, I am subtracting standard deviation from mean. So 0.34 minus 0.18. As you can see that in the question we have the value that the mean is 0.34 and standard deviation is, or the variance is 0.18. In fact, I should have written here that this is not variance. Pardon for a little bit of typo. So I write here standard deviation. So standard deviation is 0.18. So let me repeat, the question says, can we conclude that this set of 34 values follows normal distribution with mean equal to 0.34 and standard deviation is equal to 0.18? So what I have done is, I have written the value of mean here in this cell just for convenience and standard deviation here in this cell. So mu minus sigma means 0.34 minus 0.18. Similarly, mu plus sigma is 0.34 plus 0.18. So we come up with this limit. So this is my 1 sigma interval or 1 sigma limit. So if this distribution is normal, then according to this diagram, now coming back to this diagram, if this distribution is normal, then we should have 68% of the data between 1 sigma limit. And how I can check here in this example? You see, my 1 sigma limit is 0.16 to 0.52. So if I am solving this question manually, then I am going to visually scan how many values are between 0.16 to 0.52. So either you have to count manually or you can apply some filter in Excel, and you can see that there are 6 values in this data between 0.16 to 0.52. Suppose if I have to check, use the Excel filter, so I can simply go conditional formatting, highlight cell rules between, and I can say values between 0.16 to 0.52. So I have told that this is my highlighting rule. You can pick up different types of rules here. Either you can have yellow fill with dark yellow text and so on. Anyhow, so if I press OK, you can see that these are 1, 2, 3, 4, 5, 6 values. So there are 6 values within 1 sigma. And how many total values were there? As I told you in the start, that these are 34 values. Right? These are 34 values. So how many, if I have to compute this, the percentage, so 6 out of 34 means roughly 17%. So if this distribution was normal, then this percent should have been 68%. But here you can see that this is not 68. So just by constructing the 1 sigma limit, we know that this data is not normally distributed. Now suppose that in any other question, this percentage came out to be close to 0.68 or 68%. So you would have concluded that one check about the normality is met. But then you should have also checked about the 2 sigma limit, and it should come up with 95%. Similarly, 3 sigma should come up with roughly 100%, because practically all data is covered between 3 sigma. So by using this example, what I have told you, that how you can construct the sigma limits, how you can count the frequency within those limits and convert that frequency into a percentage, and then match that percentage with the threshold for the normal distribution. So if the 1 sigma limit percentage of values within 1 sigma limit is 68%, and percentage of values between 2 sigma limit is 95%. Similarly, percentage of values between 3 sigma limit, if it is approximately 100%, then this distribution can be declared as normal, right? So this is just one type of a check. Now we will be talking about the upper and lower range of Z. So researchers have proved that if you put the value of x is equal to mu minus 3 sigma, you see, if I put the value of, this is my standard normal variable. So if I put, x is equal to, coming back here, put x is equal to mu minus 3 sigma. So what will happen? If I put x is equal to mu minus 3 sigma and then solve this equation, you will simply see it will come out to be minus 3. right? I'm putting here mu minus 3 sigma. If you put x is equal to mu plus 3 sigma, because that's the upper limit I just defined for the normal distribution. So if I put x is equal to mu plus 3 sigma in the standard normal variable, the upper limit will come out to be 3. So the lower and upper limit for the z distribution or the z is minus 3 to plus 3. So this is the reason earlier on I was telling you why this table is ending at 3, because the upper limit for z is 3 and the lower limit is minus 3. So up till now we have discussed important properties of normal distribution. Next I am going to help you understand further the upper and lower limit of normal distribution. So let's say we want to analyze that almost 50% of the data is covered between 0 to 3.0. So how I can check? If you refer back to this table and if I read this table for z is equal to 3.0, you can see the value is 0.4987. This is exactly I have written here. Refer me back to this table. So I am reading it for 3.0, the value is 0.4987. So table value for z is equal to 3.0 is 0.4987. So area between z is equal to 0 up till z is equal to 3.0. So whenever I read the table for a given value, given positive value of z, it gives me an answer or the area between z is equal to 0 and z is equal to particular value for which I am looking. Now we know that the normal distribution is symmetric. So area between minus 3 to 0 is also 0.4987, right? If you don't understand here the concept, coming back to this normal distribution, so if we have all the negative values are towards the left hand side and the positive values are towards the right hand side. So when I talk about symmetry, it simply means that area between 0 till positive value is same as area from 0 to same negative. For example, 0 to plus 3, then the same value will be 0 to minus 3. So the table gave me the answer for z is equal to 3.0 equal to 0.4987. So I can say that area between minus 3 to 0 is also 0.4987. So if I have to find area between minus 3 to plus 3, it is equal to 2 times 0.4987, which is, you can say, roughly 100%. So now you can see roughly 100% of the data is covered between minus 3 to plus 3. That's why we said that the lower limit for z is minus 3 and the upper limit is plus 3. So this discussion has helped us understand an empirical rule that in normal distribution, roughly 68% of the data is between one standard deviation limit, 95% of the data is between two standard deviation limit, and roughly all the data is under 3 standard deviation limits. So next we do some numerical example that will help you understand the idea of normal distribution further. Given a standard normal distribution, find the area under the curve that lies to the right of 1.84. So if I, for example, I draw this bell shape, and we know that in the center z value is always 0. Let me refer you back to this diagram. You know that in the center we have mu. So if I put x is equal to mu, the standard normal variable will become, for example, here I put x is equal to mu, so z will become 0. So we have the central value as 0, and we have to find the value or the area or the probability towards the right, so I've shaded that as blue. So what I'm going to do, I'm going to refer to the normal table and I'm going to read it against the value 1.84. And how am I going to do? You can easily see I have taken a screenshot of that table and pasted here. You can see that I have referred to the row having the value 1.8 and the column having the value 0.04. Why? The first decimal place, if I focus on this z value, up till the first decimal place this value is 1.8. So in the row I'm looking for 1.8. In the second decimal place we have 4, so I'm going to focus on this column having 4 in the second decimal place. So this gives me 0.4671. But this table is constructed in a manner that if I read it against any value, it gives me answer from 0 up till that value. If you, for example, let me take you to the heading of that table as well. This is the table whose screenshot I took. So you can see that right over that table they have drawn this bell. So whichever normal distribution table you are using, they always show that how that table is constructed. So this table is constructed in a manner that it gives the answer from 0 up till some value. So if I read it, the table that I have just discussed against 1.84, it gives me the answer 0.4671. But so this is the answer for this area, but I am looking for the area here, the shaded blue part. So we know that half of this bell is 50% or 0.5. So I am going to subtract this number from 0.5 and I'll get the required area. So the required area is equal to 0.5 minus 0.4671. So this is one numerical example where we use the standard normal distribution table and we computed the required area or required probability. Another example where we are going to compute probability between z is equal to minus 1.97 and z is equal to 0.86. So if I have to compute this probability, so this is the bell shape. We know that the negative value is towards the left of 0. So for example, if this is minus 1.97 and this is 0.84, so we have to find area between these, so that's why I have shaded this entire area as yellow. Now let me solve this example step by step. First let me focus on negative 1.97. We just saw that the table I was discussing, it is giving me only the positive values of z. So I'm going to use these positive values of z and I can easily find the required data. How? For example, if this is minus 1.97 and we know that area towards the left of minus 1.97 will be equal to area towards the right of plus 1.97. So this is the basic definition of symmetric distribution. So if we have whatever the area here before this negative number, the same area will be towards the right of positive part. For example, if this is minus 1.97, so if I take it positive, it will be 1.97. So if area toward the left of negative 1.97 will be same as area towards the right of 1.97. So what I am going to do, as the table is not available for negative values, so I am going to read the table for 1.97, that is positive 1.97, and I will simply subtract it from 0.5 to get the required area, which is 0.4756. So here let me once again reiterate, we were looking for this area 0 till minus 1.97, right? We are looking for this area. So if I know that a value from 0 to 1.97 is equal to 0.4756, This is if I read the table against 1.97. Let me take you to the table instead of that may make you a little bit confused. So if I go to the table and read it against 1.97, let's go to the table, read it 1.97. So this is 1.9 and against the 7, which will be, if you see the third last column, so 1.9 and the third last column is 0.4756. So this is equal to 0.4756, but I was looking for this area here. So 0.5 minus 0.4756 is 0.0244. So by using this split-wise graph, I have filled that this value is equal to 0.0244. But I don't need this area, I need to find this yellow part, right? So the entire yellow part consists of two, the first yellow up till minus 1.97 till 0. So we know that 1/2 is equal to 0.5 or 50%. So if I subtract 0.5 from this number, I will have the area between 0 till minus 1.97. So 0.5 minus 0.0244 is equal to 0.47561. So now I have this area. Now for the positive, it's very easy. I am simply going to read the table against 0.84 and it will directly give me the required number. So the required area is adding these two. So by using this example, you can always keep in mind that whenever you have to find the area between 0 till a negative z, so you simply read the table for positive value of z and you subtract it from 0.5 as we have done here. So we read the table and we subtracted from 0.5, we got the required probability, but we were not looking directly for this left tail. So once again we subtracted from 0.5 because we were looking for this yellow part here. Okay, another example, given that x follows normal distribution with mean is equal to 45 and standard deviation is equal to 2. Find the probability that x takes on a value between 40 and 42. So we know that the mean is 45 and standard deviation is 2. So instead of mu I have written 45 and instead of standard deviation I have written 2. So I am going to compute two values of z. So the first value of x is 40 and the second value is 42. So once I am going to put x is equal to 40. So this is x minus mu over sigma, right? So for the first value of z I have put x is equal to 40, mu is given in the question 45, sigma is given in the question 2. So we have computed two values of z, and by using the point of discussing this particular numerical is that when you have to compute the probabilities and data given is in the form of x, you need to standardize it first and then use the table. So the data was given in the form of x or the actual variable, so I have standardized it first by using the z transformation that we have just discussed. So the z values are minus 2.5 till minus 1.5. So we need the area between minus 2.5 to minus 1.5. So and how am I going to do? I just told you that if I read the table for plus 2.5 and then I subtract it from 0.5, then it will give me the area here in this tail. So this area is equal to, let's read the table for 2.5. Let's go back to the table and you see for 2.5 the number is 0.4938. And why am I focusing on the first column? Because in the second decimal place we don't have any number. So 2.5 can be simply said as 2.50. So for 2.5 the table gives me 0.4938. So this is exactly I have put here. 0.5 minus 0.4938 is equal to 0.0062. Similarly, if I read the table for minus 1.5, read the table for plus 1.5, it will give me the entire area toward this tail. As I've just told you that whenever we read the table for positive number, for example this is minus 1.5, but if I read for 1.5, it will give me towards the entire left side here. So this area is 0.0668. So if you don't understand, just go and refer back to the table and read it for 1.5. Right? Read the table for 1.5. So 1.5, the value is 0.4332. So this is exactly I have written here. Right? 0.5 minus 0.4332. Similarly, just like we subtracted from 0.5 for the case of minus 2.5. So whenever we are using negative numbers, we are subtracting from 0.5. Anyhow, so but the required area is this orange part. So if I, this big part, if I subtract this part from here, I'll be left with this, right? This is full area answer equal to 0.0668. So if I subtract 0.0668 and 0.0062, so this is exactly I have written. The required area is 0.0668 minus 0.0062. So from this complete bigger chunk, I subtract this smaller chunk and I am left with this shaded part. Right? Similarly, we do some other examples using the table. Let's say we have to find the area towards the right of z is equal to minus 1.19. So we have the z value minus 1.19 and we have to find the entire area which is towards the right. So that's why the shaded part is all area towards the right of minus 1.19. So I told you that the table is not available for negative values. So if I read it for 1.19 but I need to subtract it from 0.5, I've just explained in the previous example as well. So if I read the table for 1.19, it gives me 0.3830. Let me refer back to the table 1.19. So you can see 1.1 and 9 is the last column here. So 1.19, so it gives me 0.3830. So 0.5 minus 0.3830, this gives me 0.117, but this is giving me the answer for this 0 till minus 1.19, but I need this later part as well. So we know that the later part is just 1/2 of the bell shape. So the later part is equal to 0.5. So either I can find, if I have to find the area towards the right, so I'm simply going to, add 0.5 here. Here I've written 1 minus, so that's just a typo. You can't simply add, area from 0 to negative 1.19. We just concluded that it is equal to 0.117. So just a minute. Okay, so I'm going to pardon, there was a little bit of a need for improvement in my explanation, so I'll explain again. So we read the table against minus 1.19 and as I said that the table is not available for the negative values, so I'm going to read the table for positive 1.19, but that will give me the answer for this left tail. So I subtracted from 0.5 to get 0.3830. So if the table gives me the answer, the positive value, if I go 1.19, so against 1.19 the value is 0.3830. right? The value is 0.3830, but we have to subtract it from 0.5 to get the answer equal to 0.117. So we get this white part here, but we don't need this white part, we need the yellow part. So the full area under the curve is 1. So 1 minus this white part, whose answer we have just concluded, it is equal to 0.117. So 1 minus 0.117 equal to 0.88298. So this is the area towards the right of z is equal to minus 1.19. So next we are going to learn the inverse use of the normal table. So for example, we have to find a value of x for a corresponding probability. For example, if we know that salary is normally distributed with a given value of mean and standard deviation, and we have to find an interval within which 45% of the people are earning. So you will understand this concept by using this numerical example. Given that a distribution is normal with mean equal to 40 and standard deviation is equal to 6, find the value of x that has 45% of the area to the left. So this is the distribution here, and now instead of finding the probabilities, we are given that the probability is 45% here. And why? We are looking for a value of x that has 45% area towards the left. So if this is the value of x for which we are looking for, it has 45% area towards here. But in order to use the table, we know that the table gives me value from 0 till x. So this is the central line, which is 0. So if this is 45% data, then this yellow part should be 0.5 minus 0.45, because this is just 1/2 of the bell. So this is 0.05. So what I am going to do, first of all, I am going to construct the z variable, which is x minus mu over sigma. So mu is given 40, sigma is given 6. Next I am going to go and refer to the table and read the table for which area is equal to 0.05. Why 0.05? I have just told you 0.5 minus 0.45, which is equal to 0.05. So I am going to go to the table, and instead of now looking at the row and column headings, I am going to use the inside values. So I have to look for the value which is close to 0.05 inside the table. So you can see this value 0.0478. This is quite close. I mean, the next value is also close. So we choose the one which is more closer. So if I choose this value approximately equal to 0.05, its exact value is 0.0478. So approximately it is equal to 0.05. So the row is heading for this is 0.1 and the column heading is 0.02. So I am going to write z value as equal to 0.12, but I have to attach a negative sign here. Why? Because you can see that the value here is negative, it's toward the left of the mean, right? And why is it toward the left of the mean? Of course, because up till mean 50% of the data is covered. So a value which has 45% area towards the left, of course it will be towards the left of the mean, right? So I am going to attach a negative sign here, minus 0.12, and I solve this equation that we have just constructed. So we put in the value of minus 0.12, we put in the value of mu equal to 40 and sigma equal to 6, and simply solve this equation, and we get that the required value of x is 39.28. So this is how we can use the table for by inverse method. Here's another example. If salary is normally distributed with mean equal to 50 and standard deviation is equal to 5, then the interval within which 45% of the people are earning. Suppose that we want to know which is the interval within which 45% of the people are earning. So we know that it's a symmetric distribution, so we divide 45% by 2. So we know that half of it, which is 0.225, is here and plus 0.225 is here. So of course toward the left we will have the negative value of z, and towards the right we will have the positive value of z. So let's say if I use the table for the positive value of z, so I am looking for a number which is close to 0.225. So you can see inside the table this number is quite close to 0.225. So the row heading is 0.5 and the column heading is 0.09. So for one time I put positive value and for the next I put the negative value. So you can see why, because I am looking for two values here. I need to construct the complete interval within which see the question was complete interval within which 45% of the people are earning. So I am looking for two values of salaries, the lower limit and the upper limit. So for the lower limit, because it's towards the left side, I am going to put the same value of z with a negative sign. And how I came up with this z value I have already told you. Row heading 0.5, column heading 0.09, and I was looking for 0.225 inside the table. So next I can simply solve these two equations and I'll get two values of x. So I'll get the lower limit and the upper limit for the salary interval within which 45% of the people are believed to earn. So this is how we learned the inverse use of the table as well. So this was about today's lecture. I hope that you have learned from these numerical examples, and keep watching the channel for more interesting content. As those of you who are my regular viewers, they know the fact that I like to connect with my viewers. So if you have landed first time on the channel, here is my picture. I am a faculty member at the NUST University. Currently I am serving at NUST University as an associate professor of statistics. And the reason I show this picture towards the end of the lecture is, as I said, I love to connect with my students, even when I teach them face to face. So if you are watching the video on cyberspace using the internet, you are equally important for me. So I want to connect with my audience, with my students. So this is the picture in which I participated in a cycling event. It was organized by a cycling group which is called Girls Cycling Squad to observe the Women Day for 2022. So we know that we appreciate, we want to develop an inclusive society which is, it's a cohesive society. So I participate in different these type of activities. By the way, I'm a person who tend to love nature, who tend to enjoy physical activity. So I keep on showing. I love to travel as well. So those of you who are dedicated viewer and they have come up towards the end of the video lecture, I hope you don't mind that I'm trying to connect with you. If you are watching the video and you don't have enough time, you may stop this part, watching this part. But those who are listening and they are still interested to get connected with the professor who is recording this video lecture for you, I'm Dr. Aisha Nazuf. As I said, I'm a faculty member at NUST University, and I love to travel. I love to participate in different type of activities that take me closer to nature, that help me develop an inclusive and cohesive society. So that was all about today's lecture. Thank you for watching. If you want to get these lecture slides, you can drop me an email. I've mentioned here my personal email ID as well, but if you like, I can also share my official email ID in the comment section. You can request for that if you want. Anyhow, the purpose is to get connected with you. If you want these lecture slides, you can simply drop me an email. You are welcome to watch the other playlist on this channel, and I would love to see if you post your comments and if you have any queries in the comment section, and I'll try my best to answer your queries. Thank you for watching.